Classic probability. Before we talk about probability, we need to talk about random experiments. So for random experiments, the outcome cannot be predicted with certain, but a collection of every possible outcome can be described before its performance. For example, toss a coin. Before you toss a coin, you cannot know the result. It's either head or tail, but you cannot predict it's a head for sure. But you know it's head or tail. So these are the all possible outcomes. You cast one red die and one white die. Similarly, you cannot predict the outcome, but you know all possible outcomes. For example, you know it can be 1, 1, 2, 6, 6. Sample space. So that's a collection of all possible outcomes. You put all possible outcomes together, it becomes a sample space. Now let me introduce some notation. So I'm going to use this C to represent the sample space. This little c is the one element inside the sample space. Now this big C is the collection of the elements. So that's called an event. For example, in example 2, I'm going to cast one red die and one white die. So this is C. So this is C. This is a sample space. Now this big C event is a collection of the pair for which the sum is 7. So this C is an event. So the sum should be 7. So it's 1, 6, 2, 5, 3, 4, 4, 3, 5, 2, 6, 1. So this is C. Now, if it's a failed die, everybody should know what's the probability of this event. You just count. How many possible outcomes? 36. Now inside, 1, 2, 3, 4, 5, 6. So this is 1 over 6. The probability of this event, so the pair, the sum is 7. To introduce probability, we need to talk about set. So set is a collection of the objects. So you put all the elements together, it becomes a set. For example, C1 is this X between 0 and 1. So that's in one-dimensional space. C1 is an interval. Right? C1 is an interval from 0 to 1. So this is C1. Now C2 is in two-dimensional space. X plus Y between 0 and 3. So in two-dimensional space, X plus Y equal to 0. Equal to 0, so it's this line. Now X plus Y equal to 3. So it's this line. Between 0 and 3, so all the point here. So that's C2. Now element of the set or point in set. Okay, so it's one element. So for example, 1/4 is in C1. 1/1 is in C2. So 1/4 is here. So it's inside C1. 1/1 is here. This is 1/1. It's inside C2. There is a special set. It's called a non-set or empty set. So it's nothing inside. That's called empty set. Also, you can compare two different sets. For example, you can define subset. So C1 is a subset of C2. If for any element inside C1, it also belongs to C2. For example, C1 is X between 0 and 1. C2 is X between -1 to 4. So this is -1, this is 4. So this is C2, this is C1. So C1 is a subset of C2. We can define all kinds of set operations. For example, union, intersection, complement, right? So it's a C1 union C2. You just put all the elements together. C1 intersection C2, the common element of C1 and C2. Complement, C1 complement. So the elements which are not inside C1. There is a useful tool. It's called a Venn diagram, right? Venn diagram. For example, you can use this rectangle to represent the total sample space. Don't forget the sample space. You can use the circle inside to denote one set. This is C1. You can denote this is C2, right? So this is the intersection. This is the union of C1 and C2. So this is how you use Venn diagram to represent the set operation. After we define the set, I can introduce the set function. Now, before we talk about set function, everybody knows what is a point function. The point function means what? The input is a point. Input is a number. So that's a point function. So these kind of functions, they are what we learned in calculus. You give me an x, I give you fx. Or you give me a two-dimensional point, x and y, I give you a value. So this is a point function. Now let's introduce the set function. So set function, the function that is evaluated not at a point, but for an entire set of points. So that means what? You give me a set, I give you a number. So the input is a set. So that's a set function. For example, let C be a set in one-dimensional space, and QC be equal to the number of positive integers in C. Then QC is a set function. You give me a set, I'm going to count how many positive integers in this set. For example, you give me a set x between 0 and 5. QC is 4. The number of positive integers is 1, 2, 3, 4. If C is -2, -1, then QC is 0. There is no positive integer. Now I can give you some notation. So if I do integration fx, I can do double integration fx. So these are all set functions. I can do sum over C. I can do double sum over C. So this is a two-dimensional subset of C. For example, let C be a one-dimensional set. QC is this integration. So you give me a C, I will do integration. Then this QC is a set function. Now I give you C. So it's x greater than 0, less than infinity. So you can calculate QC will be this integration. So it's very easy to get this QC is 1. If you give me another different C, I can evaluate this integral over this C, give you the value of this set function. There is a very special set function. It's called a probability. So now we should know probability is a special set function. So it is a probability set function. What is so special about this probability set function? Let C be the sample space. Let B be the collection of the subset of C. So inside this B, there are events. Now notation, I'm going to use P to denote the probability. So that's a convention. The P is a probability set function. It is a special set function. It must satisfy these 3 conditions. First, probability of C should be non-negative for any event. So probability is non-negative. So we don't talk about probability of something is negative 200%. That's wrong. That's not a probability. Probability is always non-negative. Probability of this sample space of all possible outcomes. Probability of all possible outcomes is 100%. So it's 1. The third condition, if Cn is a sequence of set in B, and Cn is empty set, so there's a lot of sets. Now, any 2 of them, if you do intersection, there is no overlap. Then the probability of union of this set is the sum of individual probability. So this is a very important property. But you need to be careful. The intersection, there is no overlap. Intersection is empty. If this is true, the probability of union is equal to sum of individual probability. If a set function satisfies these three conditions, we call this set function is a probability set function. A probability set function tells us how the probability is distributed over the set of events. We will often drop the word set, and refer P as a probability function. The P is a probability. Now, for the probability or probability set function, it has some nice properties. So all these nice properties, they are derived based on the definition of probability. So it's based on these three conditions. So we know these three conditions, so we can derive some nice properties of probability. For example, for any event, probability of C is 1 minus probability C complement. Why this is true? For example, you can see C, the total sample space, is C union C complement. Also, we know C complement is empty set. Now, by the property 3, probability C union C complement is probability C plus probability C complement. So this is a probability total sample space. This is 1. Now, here we get this result. Now, for other theorems, we can establish similarly. Probability empty set is 0. If C1 is a subset of C2, probability C1 is less than or equal to C2. For any event, probability is between 0 and 1. So we don't talk about the negative probability. We also don't talk about probability is 200%. That's not a probability. Probability is always between 0 and 1. We also have this nice exclusion-inclusion formula. Probability C1 union C2 is probability C1 plus probability C2 minus probability C1 intersection C2. If you draw a Venn diagram, this is obvious. So this is C1, C2. So probability C1 plus probability C2, now you count this twice. You need a minus probability C1 intersection C2. That's an intuition for this inclusion-exclusion formula. After we introduce the probability, we can talk about conditional probability. So conditional probability, the definition is conditional probability of event C2 given the event C1. So provided probability C1 greater than 0. So that's a notation. Probability C2 given C1. This is the definition. So the numerator is the probability C1 intersection C2. Denominator is probability C1. So this guy is called conditional probability. It is a probability. It satisfies all properties of probability. For example, probability C2 given C1 is non-negative. Probability of this union, as long as they are mutually exclusive, no overlap, is the probability of each individual one, sum of individual one. But they are all conditional probabilities. Probability C1 given C1. So we know C1 happens. Now what's the probability C1? Of course, it's 1. You also can verify this by definition very easily. So this is the definition of conditional probability. We know C1 happens. What's the probability of C2? For example, this is a random experiment. 5 cards from 52 cards. I'm asking you to compute conditional probability of an all spade hands C2, given that there are at least 4 spades in hand C1. So probability C2 given C1. By definition, the numerator probability C1 intersection C2, denominator probability C1. Now let's calculate the probability C1 first. So at least 4 spades. So that means you have either 4 spades or you have 5 spades. Now 52 choose 5. These are the all possible situations. 13 choose 4, so you have exact 4 space. 39 choose 1. You have 13 choose 5, exact 5 space. Now probability C1 intersection C2. So C2 is 5 space. C1 is either 4 or 5. So C2 is a subset of C1. If you do intersection, it's probability of C2. Now C2, 5 space. 52 choose 5. 13 choose 5. We can calculate the probability. So for this example, we use the definition of conditional probability. Based on the definition of conditional probability, we can define something called the multiplication rule. So this is a useful rule. It calculates the probability C1 intersection C2. So this is probability C1 times probability C2 given C1. So this is based on definition. Equal to probability C1 intersection C2, probability C1. Now let's take a look at this example. 52 cards. Compute the probability that the third spade appears on the sixth draw. In fact, this is not an easy problem. The third spade appears on the sixth draw. Think about it. Now we can solve this problem by conditional probability or multiplication rule. Let C1 be the event of 2 spades in the first 5 draws. Let C2 be the event that spade on the 6th draw. We want C1 intersection C2. So we represent this event by C1 intersection C2. Now probability C1 intersection C2 is probability C1, probability times probability C2 given C1. So this is probability. What is probability C1? 2 spades on the first 5 draws. So 13 choose 2, so 2 spades. 39 choose 3. Now we have 52 choose 5. Now we already know in the first 5 draws we have 2 spades. We know this event. Now what's the probability the spade on the 6th draw? So it's 11 over 47. So we have 47 cards left. So we can calculate probability. We can extend the multiplication rule to 3 sets. The probability C1 intersection C2 intersection C3, this is equal to, we can combine this together. Now we can apply the multiplication rule. Now for this one, we can apply the multiplication rule again. So this is extension. We can extend it into any number of sets. Let's talk about the Bayes theorem. The Bayes theorem is very important. You know, in statistics, there is one philosophy, it's called Bayesian. Now, to talk about Bayes theorem, let's talk about the law of total probability first. Suppose we have k mutually exclusive and exhaustive events, C1, C2, Ck. So mutually exclusive means there is no overlap between any 2 of them. Exhaustive means you put all these events together, it's a total sample space. Okay. So if you give me any set C, the probability C is equal to this guy. This is very easy to see. For example, I can use a Venn diagram. So this is total sample space. I can have a set. So this is C1, C2, C3, C4, C5. So K is 5. So they are mutually exclusive. There is no overlap. If you put them together, it's a total sample space. You give me any event, C. So probability C is the probability of this guy. This guy is just the intersection of C and Ci. Now probability C intersection Ci by its multiplication rule is this guy. Probability Ci times probability C given Ci. Now, after the law of total probability, we can talk about the Bayes theorem. The Bayes theorem, we need to flip the order. We don't want to know probability C given Cj. Instead, we flip the order. We want to know probability Cj given C. Now, by definition, this numerator probability C intersection Cj, probability C. So denominator, this is law of total probability. Those numerator, this is a definition, multiplication rule, probability Cj, probability C given Cj. So this is a base thing. We can take a look at an example. There is a bowl C1. It includes 3 red and 7 blue chips. Bowl C2, it has 8 red and 2 blue chips. All chips are identical in size and shape. A die is cast and C1 is selected if 5 or 6 appear. Otherwise, C2 is selected. Compute the conditional probability of bowl C1 is selected given that a red chip is drawn. So we know there is a red chip is drawn. Now ask you to calculate the probability C1 is selected. We flip the order. So probability C1 given C. C, that's a red chip, is drawn. So by the base theorem, the numerator, probability C1, probability C given C1. This is law of total probability. So probability C1. The C1 is selected if 5 or 6. So it's 2 over 6. Given C1, what's the chance you get red chip? Given C1, what's the chance you get red chip? 3 over 10. Similarly, you can get a probability C2, 4 over 6. Given C2, what's the chance you get red chip? 8 over 10. Now you can get the probability. So this is how we apply the base theorem to calculate this conditional probability. Next, let's talk about independency. Now, independency, what's the meaning of independency? So C1 and C2 are independent. So that means you know C1 happens or you don't know C1 happens. The probability of C2 does not change. So probability C2 given C1 is equal to probability of C2. So that means C1 and C2 are independent. So by definition, C1 and C2 are independent if and only if probability C1 intersection C2 is equal to the marginal probability, probability C1 times probability C2. So this is by definition. Since this conditional probability is a probability C1 intersection C2, probability C1. Then you can get this condition. So this is the only condition you can show C1 and C2 are independent. There is an interesting theorem. If A and B are independent, then A and B complement are also independent. Now, if A and B are independent, that means A intersection B is probability A times probability B. You want to show probability A and B complement are also independent. So that means you need to show probability A intersection B complement is a probability A times probability B complement. So what we know? So probability of A is equal to probability A is equal to probability A intersection B plus probability A intersection B complement. So probability A intersection B complement is equal to probability A minus probability A intersection B. So this is probability A minus probability A probability B. So this is equal to probability A 1 minus probability B. So this is probability A probability B complement. So this is how we can show if A and B are independent, then A and B complement are also independent. Now independency, C1, C2, C3 are mutually independent if only if the pairwise independent. And this guy are also independent. So this is if we have 3 events or 4 events, we talk about the independency, right? We can discuss mutually independent. Okay, mutually independent. So they are pairwise independent. Also, we have this 4th condition. C1 intersection C2 intersection C3 is equal to the product of marginal probability. Many combinations of these events and their complements are also independent. As long as there is no overlap, they are independent. For example, this event only contains C1. This event contains C2, C3, C4. If we know C1, C2, C3, C4, they are mutually independent. So these events, they are independent. So these events, there is no overlap. They are mutually independent. I will leave this as an